that was it.
Forget. So, I had just a couple of things I wanted to go over. So, tonight is the LSC Club meeting, and we've got Paul McCreary and Derek Willett that are going to come speak. For those of you that are planning on going, I really want you to try to come up with, as Paul's speaking and Derek is speaking, try to come up with one or two questions that you can ask them at the end of their presentation. If we don't have questions for them, it really falls flat. And it's not that Dr. North and I can't ask questions, but it doesn't have the same meaning as if you all ask questions. So I would like you to come prepared for that. And then kind of in conjunction with that LSC Club meeting, what I was thinking, and we'll talk about it and probably firm it up tonight, is I think our April meeting would be April 13th, right? Because that would be the second Thursday in April. And what Mike and I, my husband and I, were going to do is we were just going to offer, and for anybody in this class as well, just kind of an end of the year get together, and we can do rides out to our house, or you can drive out to our house, and we would do like a barbecue at our house. So we just think that would be kind of fun to have. I think you're kind of a fun group of students, so it'd be. And so you don't have to be an LSC major to do that. This is a small enough class. I want you to feel comfortable to do that if you would like to do that as well. So, and I was telling Abby we have a schnauzer that would be good puppy therapy for you right before. And she would think that was awesome if you all would come pet her. She would think that would be a good thing. So
April 13th is the Thursday before Easter. So
are we thinking we may want to move our meeting then? Yeah. Okay. Okay, so when we revise our meeting, we will then say that's when we'll do it. So yeah, that's fine. I wondered about that.
Good thinking, because I won't be there.
Yeah, that's when I'll be leaving too. I have to work on Easter.
Okay. So we went through our second lecture of Chapter 5 on Tuesday, and we're going to do the third lecture here today. I know that it got kind of grindy there at the end, and so I apologize for that. It's just the nature of the beast when we're working out those calculations. Today should go, they're not as long of calculations today, so I think it should go a little bit better for you. And I know a couple of you worked on the homework already, and it looked like that went fine. So again, I think maybe it's a little easier if you can do it this week as opposed to wait till Sunday night, but that's entirely up to you guys when you want to do that. There we go. All right, so flow rate and capacity analysis. So for the second, so for this part of the lecture, we're going to talk about managing throughput, some levers for managing throughput. One of the things that we'll talk about today is how improving throughput actually makes a significant difference to the bottom line, and we'll kind of show what we call the throughput profit multiplier. It's kind of the first part of the lecture. And the equation for that is just where you take the percent change in profit and divide it by the percent change in throughput. Okay? And so we have an example in our textbook, example 5.7. In this example, our fixed costs are $180,000 per month. Our revenue per unit is $22. Our variable cost is $2. And so if you remember what we talked about on Tuesday, to get to contribution margin, we take our revenue just minus our variable cost, right? So our contribution margin is $20 per unit. So in July 2010, as the example that we're using, our throughput was 10,000 units. So our profit would have been that $20, our contribution margin, times our 10,000 units, right, minus our $180,000 in fixed costs. So, again, that's going to get us to our $20,000 in profit. Okay? So our process improvement team was able to increase our output by 1%. Okay? So if we recalculate our profits, we have our $20 per unit times our 10,100 units. So we've just increased it by 100 units minus our $180,000 in fixed costs gives us $22,000 in profit, right? So we've increased our profit from 20,000 to 22,000. So a 1% increase in throughput actually results in a 10% increase in profit, right? Because and the reason for that, of course, is we're running those across the same fixed costs. That's what's not changing, right? So Another way to calculate it is, so you can calculate it manually and say that our contribution margin per unit was $20 per unit, which was given in our example. And our July profit per unit, profit divided by units, is 20,000 divided by 10,000 is $2, right? And so if we want to go through and use the formula, the throughput profit multiplier, we take our contribution margin of $20 per unit and divide it by our profit per unit of $2, and it tells us we have a throughput profit multiplier of 10, okay? And so that's basically, when we come back to it, right, we're manually calculating it by comparing, okay, look, we were at 20,000, now we're at 22,000, okay? And so a 1% increase results in a 10% increase in profit, or we can use the throughput profit multiplier and say, well, when we increase, it's multiplied by a factor of 10. So our 1% times 10 gives us a 10% increase. You're going to have to there's a couple of examples, and you'll work through those, and I think you'll get comfortable with that. The gist of it is, in this example, what we're saying is basically, we have our fixed costs, and now we're running more revenue or more units across it, so therefore it gives us more bang for our buck. The other thing that is not really a part of the text here, but I think that you should understand is, if you increase your total sales, right, we think that's exciting and we think that's good news, and it is, right? But if you decrease your expenses by the same dollar amount, it actually has a better impact on your bottom line, right? Because now you're affecting that profit margin directly, right? Otherwise, increasing $1 of sales, you may only have, only 25% of that is actually going to be profit, because the rest of it is expenses. When you improve expenses, right, it's $1 for $1. When you improve that actually falls directly to the bottom line. So, if you're trying to come up with ways to be more profitable, if you can get a better control on your expenses, that you want to do both, right? You want to increase your sales, but you also want to get a better control on your expenses. Okay? Okay, so we've been talking about, throughput, all right? And throughput, capacity, and theoretical capacity. And I want to make sure that you understand the relationship that we're looking at here. Because as you start to identify in your processes where you can have improvement, right? So if you think about your throughput is the amount of units that are going through your process, right? Everybody's in agreement with that, right? The capacity is what we're saying we should be able to do, right? And our theoretical capacity says if we eliminate all of the waste, right, that's what we could really do, right? And we know that theoretical capacity is an idealized point of view, okay? So when and I think this is part of, I think it's part C of your project, it might be part D, but you're going to be asked to do throughput compared to capacity compared to theoretical capacity, okay? If your throughput, right, is close to your capacity, okay, but your capacity is much less than your theoretical capacity, okay, then your area of opportunity is going to be to eliminate that waste between capacity and theoretical capacity, right? Let's look at that. We've got kind of 4 examples of how we might look at that. So when throughput is significantly less than capacity, okay, maybe you don't have enough business. So your bottleneck is not necessarily what's going on inside your process. It's that you need more business to run through that, right? So you can have that. Your bottleneck can actually be external. So when throughput is significantly less than capacity, what you're saying is we're not getting enough business, okay? When throughput is about equal to capacity, we say the bottleneck is internal, and we need to increase our throughput by increasing our capacity, right? So now we've shifted focus and said they're about equal. So if capacity is about equal to theoretical capacity, then the existing resources are very efficiently utilized already, and extra capacity requires investing in extra levels of resources, right? If the capacity is significantly lower than theoretical capacity, that means that we've got that waste to go after, right? And so a lot of times the easy answer when people start talking about process management, they intuitively want to go to, well, we just need more pieces of equipment, right? We just need more people, we need more equipment. And that's not true unless you're in C's case, unless you're saying that your capacity and theoretical capacity are about the same. And that's kind of the philosophy that lean companies try to strive for, is improvement before investment, right? Try to get that improvement out of what you've already got before you go out and invest a bunch more in more equipment and more people, right? And so make sure you're making the most of what you have, all right? So if we get to that point where we need to increase our resource levels, right, we have some options in how we do that. We can increase the number of resource units, right? We can just add more. If we're talking about we're in a bakery and we need to add more ovens, right? That's one approach. We can increase the size. Okay, maybe I replace the ovens that I've got with larger ones that can just do more, right? Or I can increase the time of operation. Maybe I'm a one-shift operation and I want to go to a two-shift operation, okay? Or I can think about subcontracting or outsourcing, okay? Or I can speed up the rate at which we're performing those activities, all right? If I'm looking at reducing resource capacity waste, right, I should focus on non-value adding activities, right? I should look at, do I have defects, rework, and repetition? Is there a way to eliminate that? Reduce time availability because of breakdowns, okay? Reduce first setup loss. If I change over from one type of production to another, oftentimes I have to set up. I think one of the things that I worked with when I was at Pella is we would get great big metal coils of cladding, is basically what we use them for, on the outside of your window. They put metal around the wood pieces, and so anyway, we'd get that metal in these great big coils. And I mean, like the pallet would be probably a 4x4 pallet, and that pallet would weigh about 5,000 pounds, right? And so when they shipped them in, they could have probably 6 or 7 of those on a truck at the most. And so, because they're just so darn heavy. Well, the way that they're produced, the company that we bought them from, their changeover time, it was this, you just think of large equipment, and the changeover time to go from one type of roll to another was like 2.5 days for them to change over. So we had like a 6 or 7 week lead time on those coils, right? And so one of the things that they did is they worked on reducing their setup time, and they went from 2.5 days down to about 1.5 days, which is still a long time. That's a significant improvement, right? So then they were able to reduce their lead time to us because it wasn't as big of a deal for them to change over between coils, right? And same kind of a thing on the custom door production line. A lot of times the doors that you're producing can go back to like a model that we used to do a lot of maybe 15 or 20 years ago, and now we're not going to do that door anymore, and somebody wants a replacement door that's just like that, and they're willing to order the custom door. So then you've got these heads that are on your equipment that you have to change out and change over in order to get the right profiles on the end of the wood, okay? And so, there were times when we first started this lean process that could take a half an hour to an hour to change over to do 2 doors maybe that were going to be that particular type, right? And so what they were able to do is they did what's called the setup reduction event, and they were able to come up with some combinations of heads that were used often. And so those are ones that you can almost plug it in, unhook it, and take it back out, and reduce that time from a half an hour to an hour down to 5 or 10 minutes for that particular type. We still had the ones that were rarer that you had to do, that it was going to take that amount of time. But that's a significant reduction in terms of the production flow. So again, you're trying to reduce that setup time. Take some of your work to non-bottleneck resources. We talked about improvement and saying that is it important to reduce time on your non-bottleneck? Well, it is if you can then move work from your bottleneck to the non-bottleneck resources. Okay. Reduce interference waste occurs due to lack of synchronization among resources. So it's that starvation or blocking, right? So I'm the next workstation and I don't have anything to do because they're doing that setup. And so now I just have to wait, right? How can you balance that? Okay. And one of the ways that organizations do that is they do what's called a mixed schedule, right? And they have an idea of how long it takes to do a certain type of unit, and so they try to mix it up so that it blends better, right? And coming up with that blend, as the scheduling manager, if we didn't have the blend right, I'm telling you, I had managers in my office bitching. I mean, if it's right, nobody cares, right? It's one of those things. If you do it well, nobody notices. But if it's not done right, they're gonna come after you. And here's another example of that. If you think about running windows on a production line, okay, and we would do down to, I can't remember the smallest size, but let's just say 20 inches, right, up to 100 inches. Right? If every window went from 20 inches to 100 inches to 20 inches to 100 inches, every time you did anything with a press, and we have a press on both the frame side and the sash side, it's going to go from 20 to 100 to 20 to 100. And you think about how much time that takes. And so one of the things the schedules were set up in is to increment to go from smallest to largest, and then to come back down from largest to smallest, right? So that there's just this kind of small change as you're going through, right? And if we screwed that up, that's when I would definitely have people in my office going, what are you doing to me? You're killing me today, right? And so, and it was true. You could just see a significant impact on their productivity. Okay, so that's kind of that example of reducing interference waste. Okay. So once you've resolved the issues with your current bottleneck, right, you must shift your focus to the new bottleneck. So it's this ongoing process. And as we can see, it's an ongoing cycle of improvement. All right, we want to go ahead and kind of turn our attention to some things in the appendices for Chapter 5. We're going to talk about load batching, okay? So that's where resources can process several flow units simultaneously. I always think, for me, baking cookies is a good example of that, right? I put my sheet of cookies in the oven, and it's doing all 12 of them at one time, right? That's load batching, okay? Schedule availability. Typically, each resource unit is scheduled for operation only a portion of the time. So, again, it kind of goes back to when we were highlighting those people that maybe they were only available 6 hours a day. That's when we talk about schedule availability. Okay. All right. So when we talk about effective capacity of a resource pool, and we're talking about load batching, right? It's just a matter of getting your head around what the variables mean. So C sub I is the amount of resources that you have, right? So you just kind of need to learn to remember that from our previous work in Chapter 5. And T sub I is the average amount of time that it takes for that resource to complete its steps, okay? And so when we have load batching, right, then we need to go ahead and multiply to get to the effective capacity. We need to multiply by the size of the batch times its scheduled availability. Right? And so what I want to do is go ahead and just do a quick example. And so that's with our kind of bakery example. We've got 2 ovens, right? So that's going to be how many resources we have. So which variable in that top equation does that represent?
C sub I.
C sub I. How many resources? So our resources that we're talking about is ovens. Okay. 10 loaves of bread per batch. What variable is that?
Load batch.
That's our load batch, right? And the baking time is 15 minutes. What variable is that?
T sub I.
T sub I. And our oven operates 7.5 hours per day, or 450 minutes per day, and that's going to be our scheduled availability. So now to understand my effective capacity, I'm going to do my 2 resources divided by my 15 minutes of time that it takes for them to process, right, times my load batch of 10 times my 450 minutes per day says that I can do 600 loaves per day. So that's my effective capacity when I'm working with batches. Okay? If I have setups or changeovers, right, which is the cleaning, resetting, or retooling of equipment in order for it to process a different product, right, we're going to call that S sub I. That's the setup or changeover that's associated with a particular resource. Okay? And so then Q is the quantity of the batch size that I'm going to do whenever I do a setup, right? So note that Q is different than the load batch. Q represents how many units will be sequentially run through the process after a setup has been done until the next setup needs to be done. So maybe let's do the example with our bread, and let's say that, you know, we said that we were going to bake, we're going to make, so we can do 10 loaves of bread per batch, and let's say that we might do 5 batches in a row of bread, right? And then maybe I decide I need to do cookies instead of bread, and I need to change the oven temperature, so then that's a setup, right? I have to turn the temperature down, let the ovens cool down or heat up, whatever that case may be, right? And so as I can do 10 at a time, maybe I'm going to do 5 runs of that, so my Q would be 50, right? And then I'd have a setup, okay? And so a load batch represents how many units can be done with each load, all right? So again, that's kind of that difference between the setup and the, or that Q and the load batch. Okay, so what we need to get to then is we have to somehow account for that setup time in order to have an appropriate effective capacity calculated, right? If we've got setup involved, we have to include that somehow in our time calculation. So what we do is we adjust our total unit load calculation to include the time that it takes to process, right, plus the S sub I, which we said was the setup time, divided by the Q, which is going to be the quantity of how many we're going to do before we move to a second setup. Okay. So to compute effective capacity, we replace unit load with our total unit load. So now our effective capacity formula goes to how many resources do we have, and I'm going to divide it by the total unit load instead of just the unit load. Okay. So these aren't hard calculations at all. It's just about getting your head around what those different variables mean, right? And it's just going to take a little bit of practice to kind of work your way through them. Okay, so then to do an example, to show, kind of an example of how that comes together. So Q is, so if I only do 5 units before I make my next changeover, right? My total unit load per minute is going to be 10 minutes, and we're going to say that it takes us 60 minutes to do the setup. And I'm going to divide that by 5, which is how many units I'm going to do before I do my next setup. So that means that my total unit load is 22 minutes. Okay, so my capacity then is the inverse of that, right? So 1 over 22. Okay, and so my capacity in terms of units per hour, I'm just going to multiply by 60 minutes per hour. It tells me that I can do 2.7 units per hour. So to get from once you get your total unit load, all you're doing is the inverse of it to get to capacity. Same stuff we've been doing all the way through Chapter 5. And then I'm just converting to units per hour, so it's a measure that makes some sense to us, right? But if I increase, since what we're trying to show here is if I increase my Q size, my load batch size from 5 until 10, right, then I get to 3.75 units per hour. If I go from 5 until 20, right, so now I'm going to do 20 units is my load batch size before I change over. Then it gets to 4.6 units per hour. If I go up to 60, then it's 5.4, 125.7. So it's just common sense, right? If I increase the number of units that I run before I change over, right, that increases my capacity, okay? Because I'm not changing over as often and I don't have as much downtime because I'm doing that changeover. And there's a couple of ways to kind of approach that capacity to try to increase your capacity. One of them is this, increase the load batch size, and the other is reduce the amount of setup time. And they basically accomplish the same thing. So that was kind of the end of the problem reviews, that was the end of the review for the appendices. And what I thought I'd do is go ahead and kind of pick up, there's a couple of problems at the end that we didn't get to on Tuesday. These are a little bit more straightforward than the one we were working on. So I'm going to go ahead and set up to do those on a blank spreadsheet. I'll go ahead and blow that up a little bit so it's a little easier to see. And if memory serves me correctly, Did we finish 5.3? Is that where we have gotten to?
We were on 5.4.
What we did do?
Yeah, we finished it, like, the very last one. It's like if you changed, like if you moved the billing to the receptionist.
Yep, okay. All right, so this one, we're going to, so we're going to do 5.4, let me see, we're going to do 5.4, 5.5, 5.6, and 5.7. 5.6 and 5.7 are real short and sweet. So 5.4 kind of takes us back to what we were working on from Tuesday and is just another example of that. So a company makes two products, A and B, using a single resource pool. The resource is available for 900 minutes per day. The contribution margin for A and B are $20 and $35 per unit respectively. The unit loads are 10 and 20 minutes per unit. And then it says which product is more profitable. So just as a recap, we worked on some problems. I'm going to flash one of those back up here. Right? We worked on kind of this longer problem. And when we answer the question, which type of project is more profitable, right, we have to look at each product individually in order to get to its capacity individually. Okay? And so, but when the question then asks, what about the capacity of the process overall, that's when you have to combine them up and get to that artificial unit load. Okay? And so as you're working on a problem, you need to decide, am I looking at each product individually, or do I need to combine them up and get to an artificial unit load? Okay? I just kind of wanted to re-emphasize that. All right. So for 5.4, then basically I'm just going to kind of capture the information. We have product A, right, and product B. And we are given the unit load for each of those, right, because unit load is minutes per unit. Everybody on board with that? Okay. And if that's the case, then what it tells me is that I have 10 and 20 minutes per unit, respectively. And it's probably maybe if I do it like this. No, we're going to leave it like that. And then I'm going to do contribution margin, because we're given that information as well. And so contribution margin is $20 and $35 respectively. Okay? And I just kind of like to capture all the information in one spot before we go too much farther. And so the other thing it tells me is the resource is available for 900 minutes per day. And so I'm just going to make a note. Resource is available for 900 units per day. Okay? So the first question is, which product is more profitable? Okay? So in order to calculate that, right, we would look at this originally and we'd say, well, the contribution margin for product B is higher. But based on what we learned on Tuesday, we know that that's not sufficient, right? We need to look at contribution margin per unit of time, okay? And so in order to do that, I have to get to what the effective capacity is for each one, right? And our effective capacity is, how do I calculate that? I have unit load, and to get to effective capacity, what do I do?
1 divided by unit loads.
Yep, 1 divided by 10 in this case, or 1, so we just take the inverse of it. That's something that I would hope you guys are starting to make that connection. I go from unit load to effective capacity, and I take the inverse of the unit load. Okay, so Then what I do is I say, well, which product is more profitable? So I need contribution margin per unit of time to determine that, right? And so for product A, it's going to be $20, right, per unit, times I can do 0.05, excuse me, for product A I can do 0.1 units per minute. And so if I do the math on that, $20 times 0.1 is going to be $2 per minute. And for product B, I have a contribution of $35 per unit times 0.05 units per minute. Gives me a contribution margin of $1.75 per minute, right? So then product A is our more profitable. All right. Then the next question, part B, says the company wishes to produce a mix of 60% A's and 40% B's. What is the effective capacity in terms of units per day? All right. So I have, so we've done our which is most profitable. So to get to the effective capacity of the process, what do I need to do? What's the first thing I need to do? Can I use the individual products? I can't, right? So what do I have to do? So I need to create an artificial unit load, okay? So in order to do that, right, I'm going to come down here and I'm going to say, okay, my unit load in terms of minutes per unit for A, and my unit load in terms of minutes per unit for B, right? And those were 10 and 20 respectively. And we're saying that we want a 60% mix of A and a 40% mix of B. So then my artificial unit load is going to be 10 times 60% plus 20 times 40%. So that tells me that my artificial unit load is 14 minutes per unit. Okay, so now that I have my artificial unit load, what do I need to do to get to my effective capacity of that resource? So that's 1 divided by 14. So that says it's 0.07143. And then to get to the effective capacity of the resource pool, I have to document how much that resource is actually available. If you remember, they told us it was available for 900 minutes, right? And so I'm going to take 0.07143 times the 900.
How did you get the effective capacity again? Effective capacity resource?
It's the inverse of the unit load. Okay. All right. And so that's the effective capacity of our resource pool. So again, we have to develop the artificial unit load. We have to find the effective capacity of one resource, and then we have to apply that effective capacity of one resource times the availability of that resource. Okay?
So you just multiplied for the...
Mm-hmm. All right, then it says, what's our profitability per day? What I'd like for you to do is work on that for just a quick second, see what you can come up with. I'll be right back. I need to go do something real quick.
Per day. was the question you just wrote down?
The effective capacity
Of
per day, of units per day.
Okay.
We just got this. Not still in minutes. Oh, it's units.
Capacity per day of the resource pool per day.
Of, units per day.
What are you confused on?
How it's per day.
Yeah, because I guess that's the mix they're going to do in a day.
Okay.
Because if you wanted it, like, you could resource pool, and then if you wanted it monthly, you take it times how many times.
Gotcha.
So that's per day.
And then they're asking for the profitability. Which I don't look at per day.
Are we done right now? I just want to ask which one is more profitable per month. And you take the CM times the lowest effective capacity of the month.
Yeah, and then it gives you. With our contribution margin, was that per unit?
This is, the effective capacity that we just did. This is per, I guess, technically day. So then we need to take that by how many days in the month. And then that times our CM. But no, we can't do that. We're going to have to break it out because this is the this is combined.
So if we're trying to get to the profitability, right, we're going to take that contribution margin that we were given per unit. So we were told that it was $20 and $35. And we need to come up with kind of our trying to think what I would call it. I guess your weighted average of your contribution margin. And so basically that's going to be $60 times the $20, right? Plus 40% times the $35. And so that tells us that our weighted average contribution margin is $26, so our profit per day is going to be the effective capacity of the process times that contribution margin. So $1671.43. Did you guys kind of get there on your own, or did you get stuck someplace?
And we needed the contribution margin.
I got that, but I didn't get that like you got that.
Okay. How'd you get it, Abby?
I took the effective capacity and I multiplied it like by 60%, and then I multiplied that by $20, and then I
Took the remainder. So basically you did the same thing, you just worked the math in a different way, basically. So it's the same effect of how I took the contribution margin and did it, but you actually took the effective capacity and said 60% of it is for product A and 40% of it is for product B, and then took that times.
and I just added it together.
Yep, and that works. That works.
So can you show me how you get the 26 again? Just like click on this.
Yeah, so it's a weighted average. So it's 60% times $20 plus 40% times $35. So
Okay, so it's like the same thing you did with the artificial capacity, but with this
Mhm.
contribution margin.
with
instead of-
contribution margin.
Okay.
Mhm.
And then you just took that times the effective capacity to get, and that is your profitability.
Mhm. And there's nothing wrong, Abby, the way you did it is perfectly fine. It's one of those things, there's more than one way to think through how to get there, and so that works just fine the way you went as well. Okay? So that's problem 5-4, and I think that's kind of a good example of, okay, well, we're being asked questions about each individual product, then we're being asked questions about, I'm sorry, Julie, did you need that? So we're being asked questions about each individual product, and then we're being asked questions about the process. So each individual product, you have to calculate effective capacity individually. And when you're talking about for the process as a whole, then you have to combine them and come up with the artificial unit load. Do you have a question?
No, it's just
Stretching. You'll laugh. So my youngest son, when he was little, he couldn't handle anything, sticky on his hands, and so he would sit in his high chair and he'd, like, get this off of me kind of thing. So my husband and I were joking this weekend because we went to see him at UK, and we're like, these are happy hands, jazz hands, right? These are sticky hands, right? And Abby, you were doing a happy hand there. That's what that looked like to me.
I was just thinking.
Okay, so that is 5-4. All right, let's take a quick look at problem 5-5. And problem 5-5 is an insurance company processes two types of claims, life and property. The capacity of processing life claims is 500 per month, and the capacity of processing property claims is 1,000 per month. Okay, so one of the key things you should recognize here is we've stepped on, we're no longer looking at unit load, we went right to looking at capacity, right? And so just make sure that you're thinking through, what we're talking about. So in terms of the life and property, we were given information in claims per month for both. And we were told that life has 500 and and property has 1,000 claims per month. Okay. Assuming a common bottleneck, what is the capacity of the process if you have a mix of 50-50 of the two types? Okay. So here's the trickiness of this particular question. Okay, so when we do artificial, are we doing artificial unit load or are we doing artificial capacity? When we're looking at the combination in a process.
Capacity.
So we're getting to a capacity, but we're using an artificial unit load. Okay, and so you can't just you can't assume that this is going to come out to be the same if you take the weighted average of your capacity. You have to take a step back, get to your unit load, and then do your artificial unit load and then calculate your capacity. Let me show you why that is. Okay, so let's do, and I'm going to hope it comes out because I didn't practice this one ahead of time, but let's just take a quick look. So, so to get to artificial unit load, right, so if I want to back up and get to artificial unit load if I want to get to unit load for life and unit load for property, what do I need to do?
The inverse.
Yep. So it works both ways, right? If I'm going from unit load to capacity, I take the inverse. If I want to revert back from capacity to unit load, I'm going to take the inverse. So it's going to be 1 divided by 500 and 1 divided by 1,000. And this is in months per claim, right? Because now I've reversed that. Bless you. Okay? And so that being the case, if this is 50-50, right? To get to my artificial unit load, to be consistent, I'm going to take 0.002 times that 50% plus 0.001 times 50% gives me an artificial unit load of 0.0015. Okay, And so then my capacity would be one divided by 0.0015, right? So this is, again, now I take the inverse to get back to capacity, all right? So here's why it doesn't work, because why it wouldn't work to just take a weighted average of our capacity, because my weighted average of my capacity would actually say that it was 750 claims, right? 50% times 500 plus 50% of 1,000 is going to get me to 750. So because the message from this problem is when you're working with that artificial unit load, you need to get the artificial unit load to calculate the combined capacity of a process. You can't look at the capacities and just take the weighted averages. You have to move it back to the unit load and then calculate it from there, okay? Because the math does not work out the same, okay? So that's really the message behind that particular problem, all right? And then last but not least, we have kind of a, I shouldn't say last but not least, let's see. We're just going to go on to 5.7, okay? And 5.7 says, re-examine exercise 5.1 and assume that the capacity waste factors of the paralegals, tax lawyers, and senior partners are 20%, 30%, and 35% respectively. What is the theoretical capacity of the process? Because now we've studied about theoretical capacity. So if I'm going to re-examine that, right, we would say that we needed to look at those three resources, the paralegal, the tax lawyer, and the senior partner. And if we went back and looked at their effective capacity of the resource pool, and I'm going to go ahead and add in, we need contracts per day. Basically, we had calculated that the paralegal could do 4.8, that resource pool could, that the resource pool of tax lawyers could do 12, and the senior partners could do 8. And from this problem, we had our waste factor for each, and it was given to us as 20%, 30% for tax lawyers, and 35% for senior partners. So then to get to my theoretical capacity of my resource pool, and that will also be in contracts per day. Okay. Does anybody remember the formula for that? So I'm trying to calculate theoretical capacity. What's the formula for theoretical capacity?
Would it be the effective capacity divided by 1 minus the waste factor?
That's it exactly. Okay. So it's the effective capacity divided by 1 minus the waste factor. And I can promise you you'll have a problem like that on the exam, and so you just need to remember what that formula is. Okay? And so then if I calculate it for the paralegal, that means the paralegal can do 6 contracts per day, the tax lawyer can do 17 contracts per day, and the senior partner can do 12, right, for theoretical capacity. Okay? So those were just, I wanted to just finish up today with doing some examples from finishing out the examples here in the back. So you'll have that, you have some problems to do from Tuesday and from today, and they should tie pretty closely to what we went over here in class. But Did you have a question, Abby?
Can you click on the equation?
Mm-hmm. Okay. So that being said, y'all have a good weekend. We'll come back here on Tuesday. We'll do an exam review, and then you'll have your exam on Thursday. Okay?